Right there. Okay. All right, thank you all for being here. Thank you, Bridget and JP, for hosting this session. Right now, I'm going to move away from the sort of baseline analysis that's used, or that we've been talking about earlier, and talk more about the process. And the process that I'm interested in is what's the composition of the gas, of fugitive gas? What would it look like if it were to leave a fracking site from depth as it percolates through water-saturated crust? There's a lot of dissolution effects. There's a lot of potential adsorption effects. And so we're really focused on looking at what would natural gas look like if it were to leak away from a fracking site. This work came together about a year ago. Kieran Sathaye and I kind of came together. Kieran's a mathematician, and he was interested in developing analytical solutions to transport equations that would look at the composition of gas at the gas-brine interface. And I was interested at this point of developing experiments that would target that exact same process. And so we came together over the past year, sort of got our bases together, worked out boundary conditions that I could actually model, or that he could model and I could do in the laboratory. And so what we're going to talk about today is basically quantifying these changes in both compositional and stable isotope effects that can occur. And I'll end the talk actually talking about some of the noble gas work that we're doing. And if you're familiar with, if you've been looking in the literature in PNAS, Thomas Dara has a really nice paper that just came out looking at noble gases to trace sources of methane. The outline of the talk is shown here. I'll talk about a little bit of the research we're doing. I'll use the example from the Barnard Shale that we have about 800 groundwater samples that we've sampled from the Barnard Shale. So I'll use that to set up the sort of problem that we're looking at. Then go into the theoretical and experimental methods that we're using, and finally the overall implications. Conceptually, the problem that we're tackling is really simple to understand. Doing the math to understand it and doing the experiments to understand it, that's extremely difficult. But conceptually what we're looking at is, imagine a bubble of gas that were to leave a fracking site, travel as a gas phase through water-saturated geologic media. There's a lot of potential for dissolution effects that can occur. We're talking about methane, ethane, propane. Those three compounds have different solubilities. Ethane and propane are the most soluble compared to methane, so they're preferentially going to dissolve into the groundwater. Isotopically, C13 methane has a higher solubility than C12 methane, so there's potential for dissolution isotope effects as well. There's essentially four processes. There's advection, is obviously the bubble is advecting away from a site. Advection is not a fractionating process. The three fractionating processes that are important, one of them is diffusion transport. This has been studied for over 100 years. It's very well understood. The idea here is that the heavier isotopolog, C13 methane, it has a lower diffusivity than the lighter C12 methane. And so if you were to have a point release of natural gas or just methane, the front of that point release is going to become isotopically depleted in methane, or in C13 methane, so it's going to become lighter and lighter as you go. That's a diffusive transport process. Adsorption transport process, this is something I've worked on for the past couple of years. We have a paper that came out earlier this year looking at CO2 adsorption isotope effects, and we've got another paper that's coming out in January that's looking at methane adsorption isotope effects. These effects are a lot more complicated than diffusion effects, but essentially what can happen is either the C13 or the C12 enriched methane is going to have a differential adsorption preference, and so that again can cause a fractionation during transport. The one that I'm going to talk about here though is dissolution isotope effects. C13 methane has a higher solubility than C12 methane, and so if you were to transport methane over a body of water, you're preferentially going to lose the C13 methane into the water because it's higher solubility. And so that front, I think of it as a chromatographic front because I'm more of an experimentalist, but that front of methane is going to become more and more depleted in C13, so it's going to get much lighter. And this is basically the premise of what we're actually working on. We have a model now that takes into effect these solubility differences in methane, ethane, and propane. I think you're all familiar with the problem at hand. I sort of outlined there's actually four potential scenarios on here for what's been termed fugitive methane. Essentially three different transport processes. The one on your left is this slow path, and there's actually two inside there. This is the big public concern. This is the least likely to happen, but I think this is what the public thinks happens, is that as you fracture in the subsurface, somehow these fractures can propagate upward and form these connections to shallow groundwater, or it can tap into pre-existing fractures, and it gives a sort of fast path conduit for natural gas from a fracking site into shallow groundwater. There's two possible types of transport within this. It could be free gas transport, or it could be dissolved gas transport. The next scenario is the fast path, and that's, it's probably likely in more scenarios where there is observed contamination, and that's that somehow this methane or this natural gas is percolating up a well casing, whether it's a poor well casing, a poor cement job, or just a higher permeability along that well casing. So that's the sort of fast path. And then natural, and maybe natural is a wrong phrase for this, but sort of pre-existing. The methane or the natural gas has always been in that groundwater, and you just didn't realize it until you started analyzing for it. Now, natural can be something that's low temperature microbial, and this is something that Barnard talked about earlier, or it could still be transported there, but just transported over geologic time, or it could have come from multiple reservoirs. In the case of northern Texas, you've got two reservoirs. You got the Barnard Shale, that's the deepest layer that they're actually targeting, and the lower temperature or lower depth, higher depth Strawn Formation. I'm not going to talk too much about our results from our experiment, or from our the project that JP is leading, but there's a poster presentation this afternoon that JP is going to talk about more of the results. This plot here just shows you the samples we've collected throughout the state of Texas. I think we're upwards of about 1,000 samples now of groundwater samples that we've analyzed in the Barnett, the Delaware Basin, and also the Haynesville and Eagle Ford Shale. And this just shows you the overall breadth of the data that we're looking at, and this really sets the stage for the process that I'm trying to understand. I'll just make one point, because it was brought up in the earlier talk of the sampling. Sampling is a big deal with dissolved gases. There's no question about it. Isoflask is used commonly. It does a very good job. The serum vials can do a good job if they're done correctly. We sort of use, I guess it's called the inverted bottle technique. I think we use a modified inverted bottle technique, where we actually pre-fill the vials in the field while they're capped, and we purge about 5 pore volumes of the serum vial through it. And I think we can talk about this offline, but there's all sorts of techniques that can be used to actually do the dissolved gas sampling, but it's difficult to get correct. We've analyzed about 800 dissolved gas samples from the Barnett, and we also have, we're looking at dissolved gas isotopes, or noble gas work as well. This shows you, and we'll talk about more of this afternoon, all the red dots here. This is a blow up into the Barnett Shale. The red dots are fracture sites. The green dots are sample locations, dissolved gas sample locations, where the concentration of methane is below 0.1 milligrams per liter, essentially trace of methane. And what it shows you is that the scope of the problem is very limited in terms of location. Here we go. There's essentially one hotspot right here where we get a lot of elevated methane concentrations above 15 milligrams per liter, but the bulk of the region is baseline. It's very low methane concentrations. Barnard brought this up earlier today. Funny enough, this is the Barnard plot. I don't think you're this Barnard, but this takes looks at the C1 over C2 plus C3 ratio on the y-axis, followed by the delta C13 value of methane on the x-axis. And what it can do is you have two general regions. You have a thermogenic methane that plots down here, and you have biologic methane that plots up here, or microbial methane. This is a compilation of all the data we've collected throughout Texas. The blue are data from the Barnett Shale. The red are from the Eagle Ford, and the green are from the Haynesville. And largely, most of the data plot either within thermogenic or within microbial. But there are these regions outside here where some of the data plots out. And that's the focus of this talk here, is how do you get to those regions out there? This plot here is by define, I made it complicated just to hit the point that it is complicated to understand how methane, ethane, and propane can be affected by transport or by mixing. These lines down here would be mixing from some idealized thermogenic methane with either methane from CO2 reduction or methane from acetate fermentation. This vertical trend right here is dissolution transport, and these lines pointing down this way would be the effect that natural gas would have if microbial oxidation were to take place. What I'm going to talk about is more dissolution transport. Now, this type of dissolution transport is simple Rayleigh fractionation, Rayleigh removal. It's based off the solubility differences between methane, ethane, propane, and also the solubility differences between C13 methane and C12 methane. And as you can see, it can have a very large effect on the C1 over C2, C3 ratio. So you can get from thermogenic methane up to this field up here, but there's a very low solubility difference between C12 methane and C13 methane. It's about 0.06%. So you can't reasonably get from thermogenic methane into the microbial field by using this sort of dissolution transport alone, this sort of Rayleigh fraction removal. You have to, Kieran calculated it out, you have to get to 10 to the minus 20th remaining methane. Essentially no methane would be remaining to finally get this value to curve over into the microbial field. So Rayleigh dissolution is not a reasonable method to change the composition of thermogenic methane to make it look like microbial methane. But that's too simplified an approach for what's actually happening. Rayleigh dissolution, Rayleigh removal is a one-way street. It's just removing methane, ethane, or propane from the gas phase into the water phase. What's happening in reality, and this is a simplification of reality, this is the white is right here is a gas phase. So this is essentially the bubble of natural gas that would be migrating to the right into the water-saturated media. And with Rayleigh removal, what you're looking at is the preferential removal of ethane and propane from the gas phase into the water phase. But what it's not taken into account of is the fact that within the water phase, there's actually a lot of insoluble gases. In some of these instances, that insoluble gas could be methane that is microbial. And so there can be an additional equilibration of gases from the water phase into the gas phase. And what that does is it really sets up a really complex interaction that can happen here in this two-phase interface. There's a strong potential for compositional and chemical changes that can occur here, and that's really what our experiments were set to look at. And we do this actually for methane isotopes, and we have a series of experiments where we've already started looking at neon and argon concentrations as well. The experimental design, again, appears simple, but it took several years to get it right. It was very difficult to do it. I can talk about the details after the talk. But what it sets up is we have a very nice way of controlling the water chemistry. So we can make water with specific dissolved gas concentrations. And we have a pressure transducer on top of it, so we actually can calculate using Henry's law what the concentration of the dissolved gases are. I can make the gas compositions in the laboratory mixtures of whatever I want. This diagram right here just shows you an example. It's just a picture of the two-phase interface that can develop actually in the most simplified possible scenario. This is a meter-long column. It's packed with glass beads. You can see down here the water-saturated media that's being displaced by the gas phase media. And even in a simplified path, you still get this complex interfingering that's actually happening right here. That's where the chemistry is happening that we're concerned with. Okay, so here's a look at what we saw from the first experiment. Now, this is elution time on the x-axis, and this is the C1 over C2, C3 ratio on the y-axis. And what you can see is at the chromatographic front, or at this two-phase interface, we actually do get an enrichment. The starting C1, C2 ratio was about 12. That's the thermogenic gas right here. And at the interface, we actually can get this value from 12 upwards to about 70 or 80. We're still within the thermogenic field, but consider this is a meter-long column. So this is something that we're actually able to do within the laboratory. Once you get past the interface, though, this is the sort of high flux region, and it looks again like thermogenic. But it sets the stage for that very first bubble, that very first release actually can be compositionally different than what it started with. We don't spend all our time in the lab. I spend almost 99.9% of my time in the lab. I do take some of the students out to some of the greatest places that Austin has to offer. And so here we are at the landfill and the sewage treatment facility. And the goal here was to get a large source of microbial methane, isotopic methane. And unfortunately, so we went to the wastewater treatment facility here, and that methane had a C13 value of about minus 48 per mil. At the landfill, we got about minus 55 per mil. We didn't have a means of compressing it. And so we did our experiment with methane from the landfill that was about minus 48 per mil, and the starting thermogenic methane was about minus 42 per mil. So unfortunately, that spread in data was just not enough to get that observable effect that we wanted. This is the carbon isotope effect we saw. Again, the biogenic methane was about minus 48. The thermogenic methane was about minus 42. There's a lot of spread in the data, but it's not conclusive at this point that we actually saw this carbon isotope effect through the transport. Again, the solubility differences are very low, but if you do the mass balance here, the number of moles of methane that would be dissolved in the aqueous phase in our experiment versus the number of moles of methane that would be in that same column, the mass balance is there so that an exchange could actually happen, but I think we're lacking that difference in the C13 value, and we've since ordered microbial methane, and that's been delivered, and we'll start those experiments in January. The model, though, and this is what Kieran's been working on, this is what shows that this potential for exchange is actually there, and this is the gas injection dynamic partitioning theory. So it's a one-up step from Rayleigh fractionation or Rayleigh removal. Dimensionless speed on the x-axis, consider this a snapshot across a column. Consider this distance. It might be easier to think of. We inject gas on the left side of the column. All the way over here on the right is where you have the fully water-saturated media. So when you're all the way on the right of this diagram, you have a column that's saturated with water. And when you're all the way on the left, you have a column that's saturated with methane. What's important, though, is that this dashed line right here shows that gas-water interface. And this shows that, at least mathematically, what we can do is we can have this region right here of gas phase methane that is isotopically identical to the starting microbial methane. So this is what really drove this was the purpose of doing these experiments, to actually document that this could happen. And so what it's setting up is that, in theory, we should be able to get this region at the gas-brine interface that looks both isotopically like microbial methane and compositionally like microbial methane. And it really sets up a complicated stage, because if you're looking at the composition of the gas as it first gets to the groundwater, what is it going to look like? And will it simply look like thermogenic gas? And I think this opens an opportunity to the fact that actually no, it may not look like thermogenic gas at all. And what it does now is it applies that we can go from thermogenic and cross all the way over into this microbial field. And so that's the real results of what we're seeing from, at least from the modeling and hopefully with the experiment come January. Now, we actually started with noble gases, but with the hot topic being the methane, fugitive methane, release of methane from fracking, we sort of retuned to methane. But we actually started this with noble gases because there's been a lot of use in noble gas to trace atmospheric sources of water, crustal sources of water, or mantle sources of gases. Now, everything I talked about with the isotope effects applies to the noble gas effects. And this is an experiment, this is real time. We did this experiment on Friday, finished plotting this up yesterday. And what you can see is a similar trend in the model. This was a water that was saturated in neon that was displaced by CO2 that coexisted with argon. So it's a mixture of gas that's CO2 and argon that's displacing water saturated with neon. And what you see at this interface right here is that the neon preferentially exsolves from the water because it's highly insoluble, goes into the gas phase. The CO2 dissolves into the water because it's highly soluble, and the argon bank actually starts developing because it's actually filling the void that the CO2 is leaving because of the solubility is so high for CO2. And so again, just like with the isotope effects, you get this very complex change in chemistry at the gas-brine interface. So the results from the experiment is that I think there's, overall, everything that you've seen earlier today is that there's excellent potential to use isotopes and to use noble gases to trace sources of fugitive methane, if it is fugitive, but there's a lot of processing that could take a role, and so we need to consider what these process effects might be, especially in the fact that, we're trying to look at these baseline conditions, and is the mobility of the natural gas, is it free-phase natural gas or is it dissolved natural gas? And I think there's a lot of opportunity for isotopes to actually play a role in here. All of these effects are fair game. I think in this case, when you're talking about transport through water-saturated crust, solubility is going to be the biggest one, the biggest player in this. And overall, it's this ability to integrate these lab experiments, these models, with the wealth of field data that's coming out of these types of studies that makes us a very good place to work right now. And I'll stop there. Thank you.
Any question for Tony?
Yes?
What about, you said the solubility of C2 and C3 relative to C1? That's why you weren't just plotting the concentration of methane, you were plotting it on the y-axis.
That's correct.
Can you repeat?
Yeah, so the question was the y-axis on that Barnard plot. It's that y-axis is the C1 over C2 C3 ratio, and so the solubility differences between methane, ethane, propane are what drive that movement of that transport process that I'm outlining. Drives it vertically because you're looking at the ratio of methane to ethane and propane. So as more dissolution occurs, you preferentially lose ethane and propane relative to methane, and that's what drives it vertically. Is that the question?
Is there any information, how helpful would it be to get the carbon isotopic composition of the C1, C2, C3?
Well, we're getting so we're doing this isotope work is actually focused on the methane. We haven't looked at the ethane and propane. It's possible. It's just a data set we haven't even begun to interrogate. I would assume at this point that the solubility of C13 ethane is also higher than the solubility of C12 methane or ethane. So it's going to be the same. Solubility at the first order is a mass effect. Sure.
What's the limit for your delta C13 of biogenic versus
I mean, it's not so much a detection limit, it's just a range. I mean, thermogenic has this range that goes all the way from, I mean, very heavy. I think the heaviest can be on the order of minus 15 per mil, down to some pretty, typically about minus 48 per mil. I mean, that's the sort of typical range of thermogenic. But that's dependent on the source material that the thermogenic methane or natural gas came from, and it also is dependent on the temperature that the natural gas was generated. But I think overall, you're looking at this sort of, minus 50 to minus 15 really opens the door for the entire range of possible thermogenic. And there will certainly be overlap with microbial, no question about it. But it's that's the power of adding the ratio of C1 to C2, C3 is so important. I mean, the ground is predominantly methanogens. I mean, there are some examples of ethanogens and propanogens, but generally, if it's microbial, they're making methane and not ethane and propane. In the back?
So, what about the effect of fracture flow on isotope fractionation bonds? Have you accounted for that?
Was that, what about fracture flow? So I think, tell me if I got the question right. You're asking what are the effects of fracture flow from depth to shallow groundwater?
Yeah, like, in your diffusion transport model, your experiments would account for any flow.
Yeah, and so I guess I'll add one more to that. How about asking, what about fracture flow if gas phase fracture flow versus fracture flow if it's complete soluble gas fracture flow? So it's simply if you start with if it's dissolved gas, so it's aqueous transport. First off, diffusion is going to be so slow that, I mean, the amount of that would be a geologic time scale for that type of water to get from the fracking site or from depth to the shallow groundwater. If you were to enhance that by some process such as pumping, maybe you can gain some advection. But if it were, importantly, as far as these fractionation effects, if it's aqueous phase flow, there's no opportunity for this exsolution or dissolution to happen. And so in those cases, then the dissolved gas is going to should look, I shouldn't say exactly, but more like the thermogenic that it started with. If it's gas phase flow along these fractures, that's where the opportunity for dissolution and exsolution to happen, that's where that opportunity is. And so I would argue if it was gas phase flow, and if you sampled it right as that initial front came through, that's where you're most likely to observe these compositional and isotope effects. If it's very high flux, I mean, if this thing has been flowing for geologic time periods and it's gas phase flow, then it's going to look like thermogenic gas because you've essentially changed the chemistry of the water that it's interacting with, and you're more in equilibrium with the water. But it's under these certain conditions of, and that's a concern with the public concern really with fracking, is that this is gas phase flow from a fracking site, real time within a matter of months. That's where you get most likely to get the chemistry to happen.
Thank you, Tony.
Thank you.
And this concludes the session. So I hope to see you all this afternoon in the poster hall. Thank you.